Okay, yeah. So this was the definition of P that we have defined in the last class. Now we'll start with defining the class NP. Okay, good. So, but all right. So before that, we need to, what is NP? So we are going to go about defining NP. So the thing was like, informally, if we want to say what is NP, it is problems, set of problems that have small certificates that can be efficiently verified. Okay, and by small and efficiently, both we mean polynomial time, right? So small is polynomial size and efficiently, as we know, is polynomial time. Right? Okay. So we say that, so let's say that there is a problem, right? Some problem. So, and to solve that, we have an algorithm B. So we say that B is an efficient certifier for problem X, let's say. Just a moment, I'll be back. Yeah, hi. Sorry. So we say that B is an efficient certifier for problem X if two conditions are satisfied. Okay. Okay. First is that B is a polynomial time algorithm. That actually takes two inputs. S and T, let's say, where S is the problem input for X. And second is there exists a polynomial function P such that S is in X if and only if there exists T such that B of S comma T is equal to 1, right? Or B of S comma T is yes. B accepts on S and T as an input, and size of T is less than or equal to P of size of S. So it might, and then like NP is basically just the, like, let me just write it down because set of all problems that have efficient certifier. Okay, good. So let's just go through the definition once more and see what it is trying to say. So what is an efficient certifier? So an efficient certifier is something that works in polynomial time, and given a certificate and the problem instance, it can see whether it is really a certificate or not. In polynomial time, it will verify that whether this certificate works for this problem or not. Like if you are given a satisfiability instance, then the certificate, the string T that we are here, it can be a satisfiability assignment, right? If we are given a graph and the problem is independent set, T can be just a set of vertices. Right? And what does it say? The second condition says that, okay, this the size of T is actually bounded by a polynomial in the size of S. So the certificate cannot be too big. The certificate has to be polynomial in the size of S. And the algorithm that runs in polynomial time in SNT. So it does not actually find the certificate. The algorithm, it given a certificate, it actually performs the algorithm, and then the algorithm outputs yes if and only if the string is in X, right? So this is like this algorithm B is more like a verifier or certifier. That's why it's called that, right? It needs a certificate. So sometimes it is also said that B can guess. Is theory of computing a prerequisite for this course? Can somebody tell me? Is it or it's not?
It's not.
No, sir.
It's not. Okay. You said it's not, right? Either it is or it's not. Can somebody type?
No, sir, it's not. It's a course for next year.
Okay, all right, cool. Okay, good. So that's a wrong message, it seems. All right. Anyway. So there is this thing called non-determinism, machines or such things. And what does it say? It says that there are these different kind of machines that people study. There are these non-deterministic automata and non-deterministic Turing machines, which can guess something. They can go from one place to the other non-deterministically, and now basically B can or some B prime can guess the certificate and then verify it. And this guessing is done non-deterministically. I'm just saying this because I also want to just motivate the name NP. So NP is actually non-deterministic polynomial time. So now there is just one machine which first guesses this T and then performs whatever this B does on SNT. But this machine has to be non-deterministic because it has to guess T. And actually, if you want to prove something, then you might want to go through all the strings T. So suppose we want to solve. If X belongs to or some S belongs to X or not. Okay. And for that, so now we want to use this definition for solving that. So we know that this X is in NP. But we don't know that what is T. Okay. So what is one way of solving it? So of course, it's not going to be easy to solve it in polynomial time, but how can we solve it if X belongs to NP? Any way of solving this?
Sir, what is S belongs to X?
X is some problem. Say, what is the question?
Sir, what does this mean? S belongs to X.
Sorry, there in the last class, string belongs to X is a subset of sigma star. X is called a language or a problem, and then we say that S is set of so X is also the set of strings on which we want the answer to be S. Right? So we just this is a way of abstracting out languages. So what does S belongs to X, whether X belongs to this set or not? This is the set of strings on which we want the answer to be yes.
Okay, sir.
Yeah. That makes sense or not? Like, for example, this S is going to be, suppose we want to be, we want to take satisfiability. What is this X? X is set of all strings that encode a valid satisfiability formula. Right? And what is going to be, which are satisfiable actually? So not just valid satisfiability formula, which are, but also which are satisfiable. That is going to be the set X, right? And now given any string X, we want to determine whether X belongs to, or given any string S, we want to check whether S belongs to X or not, which basically means that we want to check whether the formula encoded by S is satisfiable or not. Does this answer, Mrityunjay?
Yes, sir.
Okay, good. Right. So now suppose we are given one string S and we want to check whether S belongs to X or not. We know that X belongs to NP and we are given one string S. Check whether X, small s belongs to X. So how can we do this? We want to solve this. So let's just think of satisfiability for now. So I just told you what is going to be T for satisfiability. The T is going to be set of all possible assignments. No, T is going to be the string which is the satisfying assignment. So what can we do here to check whether S belongs to X? So we know that there is an efficient verifier, right? Or certifier, whatever, for X, right? That means if S belongs to X, so let's say the efficient verifier is B only, then there exists a T such that mod T is less than or equal to P of S, such that B of S comma T is equal to yes, right? So basically then you go through all the strings T of size at most P of S, right? And then run B on it. Run B on. So this is the first step. And second step is run B on S comma T. Give the same answer. Right? And finally, so this is happening in a loop. If B answers yes, then answer yes and stop. If B does not answer yes ever, then you can say no, because this is an existential quantifier, right? So you have to go through all the T. If for some T it succeeds, good. If it does not for any, then you say no. So you can do this, but why this is not polynomial time? This is not polynomial time because you have to go through all the strings T of size polynomial. So suppose T is binary, then you have to go through 2 to the P of S many strings. even in case of polynomial. Even in case of binary, if the alphabet is bigger, then of course we are going to go through more strings. Okay, so this was just to give you again of this thing of that what is how do we get membership in NP. We say that B is a polynomial time algorithm that takes two inputs at S and T, and if S belongs to X, if and only if there exists T such that the algorithm outputs yes on that on pair of strings S and T. Okay. Any questions? Please ask. Okay, so now the lemma says that P is a subset of NP. So how do we show that? So how do we show subsets? We take an arbitrary element of the first set. So let X belong to P. We want to show X belongs to NP. That means we want to show there exists an efficient certifier for X, right? And what is an efficient satisfier do? It has two things. So B runs on SNT. So we need to specify what B does on SNT and what is T. So we first put T is equal to, let's say, empty string. Right. And what does B of S comma T do? And again, let's say that the polynomial is again like 1, it has, or 0. Polynomial of S is equal to whatever, 1. And let's say T is just a 0, right? Something like that. So what does B of S comma T do? It just runs this. Suppose X belongs to P, so there exists some algorithm A in polynomial time that solves X. Runs basically X on S, outputs the same. Right? So S belongs to X if and only if B outputs the same, outputs yes. If and only if A outputs yes on X, sorry, S, if and only if S belongs to X, right? Because A solves X, right? So this is a simple proof, but if there is any question here, please ask. We're just showing that P is equal to N. P is subset of NP. Actually, and if you go to the non-deterministic definition that I was talking about, again, so basically then it does not require any non-determinism at all. Basically, you don't need any certificate or anything. You can just in polynomial time go and solve the problem and give the same answer. And of course, it will satisfy these conditions. Right. If there is any question about this, please ask, because this is, quite fundamental and will be, I don't think we'll need it, but this you should understand it, how we are doing it. Okay. All right. So the claim is that all the problems that we have seen, like for example, 3SAT is in NP, independent set is in NP, let's say vertex cover is in NP, And why is this the case? Why is 3 sat in NP? Let's say for 3 sat. Why is this in NP? What do we need to show for 3 sat to be in NP? We need to show that there exists an efficient certifier. So we need to show what B does and what is T. So what is going to be T? I had said it before. For S belongs to 3 sat, what can be T? Okay, is this, I'm not making this clear or what? Please, like, if you have any questions, please ask, because I'm getting less response for some reason.
So T is an assignment of the truth values.
Is T any assignment of the truth values?
It's the assignment of truth values that makes S correct. That makes
Yeah, so it's a satisfiable assignment. For the instance encoded by S. And what does B do?
It basically takes all the values in T and puts them in S and just checks the clauses if all are
Check
true.
whether S is satisfied by T. Right. So there exists as I had said in the beginning, there exists a small certificate. Why is this certificate small? Because there are n variables. So there are, you just have to for each variable, like, let's say 2n size array. Even if you want to name the number, the variable or something, or even n size is fine. And even smaller, like you can have, because you can just have log n size, just the bits 0, 1. And then you just, what does the algorithm do? The polynomial type algorithm, it takes this assignment, puts it in the formula, and sees that whether it is satisfiable or not. Okay, so now for independent set, what is it going to be? Let's say, what is T? And this you can verify that, these things actually satisfy the definition of NP. That X belongs to S, if and only if, S belongs to X for 3 sat, if and only if there exists T belonging to T such that P of S comma T is equal to yes, and T is less than or equal to 2, or let's say poly linear some order. So similarly for independent set, what can be T?
The string of the k vertices in the independent set.
Yeah, k vertices in the independent set. And B will just, take S and T. So S is basically a graph now, or comma K. S encodes a graph at least. So checks whether the vertices actually form an independent set. And similarly for vertex cover, I'm not going to write, right? So there are all these problems. And then, we have seen now that P is in NP. So seen P is a subset of NP. So question can be, are they equal? is NP subset of P, in which case it will imply P is equal to NP, right? Or there exists some X belongs to NP such that X is not in P. And this is what the P versus NP question is. And this is the, like, you know, million dollar question, like, you know, by the Klein student and so on. So is the question clear? And the belief is that P is not equal to NP. And why? Because again, like, you know, P is you have to solve, in NP you only have to, like, you know, verify. So actually verification, you know, actually solving some problems might take more time and so on than verifying. So verification would be easier. Again, this is a belief only, than actually solving. And also, even after all the years, people have not been able to show. To show any polynomial time algorithm for any NP hard problem. And we'll come to what is NP hard, but like, you know, there has been significant effort which has gone into like showing NP is equal to P, which basically any of these problems, if you show that they have a polynomial time algorithm, then they will show that P is equal to NP, right? So since I'm using these terms, let's define that also. So what is this NP completeness concept? Okay. So a problem X is NP complete if first, for all Y in NP, Y reduces to X, right? So this is called NP hard. If there exists a problem X such that, you know, any problem in NP reduces to that, then that is called NP hard. And second is X belongs to NP itself, right? So when both conditions are satisfied, then we say that X is NP complete. So first is that any problem in NP reduces to the X, and second is X belongs to NP. If only the first condition is satisfied, then X is said to be NP hard. So basically X can lie outside NP. Okay, it might not actually be in NP for all we know, right? So this is suppose, so the picture kind of looks like this, like, you know, this is P, this is NP, and then there are even bigger and bigger things, right? So I mean, that's the likely case that people believe. We don't know whether P is good to NP or not. And now there is a lemma that says, let X be NP complete. Now, if, or let's say X can be solved in polynomial time, if and only if P is equal to NP. So how do we show this? Which direction is easy?
Forward.
Actually, backward is easy, no? Because backward is just you start with P is equal to NP X belongs to NP. So X, because X is NP complete, so X belongs to P. Right? So X can be solved in polynomial time. Yeah, now tell me the forward one.
Any problem in NP will reduce to X. So, and since X is polynomial, so all problems in NP will be also polynomial. So P equals NP.
Exactly. Since X is polynomial time solvable, or let's just say X belongs to P, implies Y belongs to P, implies NP is a subset of P because Y is, and then that would imply that, I mean, along with something else. This is also along with something else. This also along with something else will imply that NP is equal to P. P is equal to N. Any question about this? So what is one like consequence of this lemma? So let's just write it as a corollary that if P is not equal to NP, then none of the NP complete problems can be solved in polynomial. So now the question is that how do we know that such problems exist? Because this seems like very exotic, right? That you take any problem in NP, whatever, and NP's definition, if you look at it, is very strange. It is just that all the problems which have certificates. So, I mean, there can be like thousands or like not just thousands, like there can be any number of problems in NP. And all of them should reduce to this single problem, right? Why can't it be that, none of them reduce? Like, suppose you have this X1, then, which is harder than like, X, X1 reduces to X2, reduces to X3, and so on. And you have an infinite chain. And this is what NP is. Then you won't be able to find any NP complete problem, right? So how can we show that some problem is NP complete? So basically, we have to look at any arbitrary NP complete problem, and reduce that to X. But what is this X? Right. So this X turns out to be this problem called circuit satisfiability, right? Which was, you can say that the first NP complete problem. Let's call it circuit sat. Okay. So what is a circuit first? A circuit is a directed acyclic graph. With nodes of, let's say, 5 type, or maybe 6 type, I don't know. First is like and, or, and not. And then you have 1 and 0. And then you have these input ones, which are at the, like, they don't have They are identified by the inputs to the circuit. These are constant, and this is and, or, and not. Okay. So they have and has two incoming edges, or has two incoming edges, not has just one incoming edge. Then there is this. And then there is an output node. With no outgoing edges. So how does it look? Let's say here you have an and, here you have an or, here you have an and, here you have a negation, let's say, and then you have an x1, then you have just, negation should have just one, then you have, let's say, or, then you have one, here you have x2. Suppose you have a negation here, you have x3, and x4, x5, or let's say 0, or 1, or let's say 0. Right, so this is a circuit basically. It is a directed acyclic graph. If so, the leaves are either a constant, the below leaves are either a constant like 1 or 0, or they are an input like 1 of x1, x2, x3, and x4. And what does this circuit compute? The circuit computes, for example, x1 not of x1 and with x2 or 1. And this all and with not of x3 or with x4 and 0. Right? So this is this formula is represented by this circuit, right? And what is circuit satisfiability? What is circuit satisfiability? Given a circuit K, let's say, find if there exists a satisfying assignment for, or an assignment, let's say for now, an assignment for the input variables which make the output node compute 1, let's say. Right? So here, this is the output node. If the output from this is 1 for some assignment, that means there is some setting of these guys such that this becomes 1. Then we say that this is a yes instance. And if for every of all of them, if it is no, then we say that no instance. So no is for all, the yes is for their exist, right? So any problem or any question about definition of a circuit? So as I said, this was the first NP complete problem. So how do we reduce any problem in NP to this? Okay, so what do we need to do for showing? So suppose the lemma says that circuit satisfiability is NP complete. Right, so what do? We basically now, so we have an instance. So now we take, let's take some x in NP. Is there a question? Please ask. So suppose we take some random x belongs to NP, right? And we need to show that x reduces to circuit sat. That means that for any s belonging to x, there exists some t, right, such that b of not such that, if and only if, I'm shortening it a bit, b of s comma t is equal to 1. And this size of t is polynomial, and b also runs in polytime. But B is an algorithm, right? What does an algorithm do? A modern computer or any such thing, it does and or not operations only, right? So what we'll do, we'll represent B as a circuit. And below, suppose we'll have this, S and T. So we'll have S and T as input, and then we'll make a circuit out of B. And whatever final node. So if there exists a satisfying assignment of B, then there exists a T such that, B of S comma T is equal to 1. And if there exists a satisfying assignment, then there exists a T such that, this becomes 1. We are not going to go into the full proof, but this is the sketch of the proof. And since we are modeling here computer programs, B, this proof actually works out. That any problem you take in NP, it has to have a certificate. That certificate you put at the bottom of the circuit. And then basically whatever the algorithm does, you simulate that in the circuit, and then you get the same output as the algorithm would have done. Okay. Any questions about this? So this is circuit sat is NP complete, is also called, Cook-Levin theorem. So this is this was the first problem, right? Because otherwise we don't even know whether such a problem should exist, not exist, and so on. But once we find this, now things become easier. That, okay, now we have one problem and we have a starting point. Remember propagating the hardness part. So now what can we do? We can propagate the hardness, and we can show that, for example, circuit sat reduces to 3 sat. I don't know whether I was using 1 or 2. And now this is not very hard, because what we'll do, so basically given an instance like K of circuit sat, we want to make an instance of 3 sat, right? So for every node, so K is a directed acyclic graph, right? So for every node V of K, add a variable xv. So let's say we want to make an instance of sat, right? So let's call it phi. So add a variable xv, right? Good. So now whenever there is a knot, right, and whatever is then below, right? So suppose this vertex was V, this vertex was U, then what do we want to say? We want to put xv is equal to xu naught, right? And how can we say that? In terms of satisfiability clauses, we can say that xu or xv or xu and xv bar or xu bar. So this means that their values cannot be the same. It cannot be 1, 1 or 1, 0, because if it is 1, 1, then this will become 0. And if it is 0, 0, then this will become 0. So they have to be 1, 0 or 0, 1. which is what is needed for xv is equal to xu bar, right? Similarly for, so first is this, second is if you have just OR of two things, U and W, should write outside. So basically what we want xv is equal to xu plus xw or xw, right? And this can be done using three of them. So xv or xu bar and xv or xw bar and xv or xw, xu or xw, right? So what does this say? This says that, okay, if xv is 0, right, that means both of them have to be 0. Because if this is 0, then this has to be 1, this has to be evaluated to 1, that means this has to be evaluated to 0. So together this implies that if xv is equal to 1, xv is equal to 0 implies xu is equal to xw is equal to 0, right? And what does this one say? That if xv is equal to 0, no, this should be xv bar. Yeah. This says that if xv is equal to 1, that means its value should be, the formula should be xu or xw, which is fine, which is what its value should be, right? So this is for OR. Similarly for AND, we can do similar things. U, W, right? And now we want xv is equal to xu and xw, and how you can do that is xv union xu bar, xv union xw bar, and of these xv bar union xv union xw. So again, you can verify that this encodes the AND operation, this collection of clauses. And that's it. So you add these, and then you add also for constants. For one, add a clause, singleton clause. XV, just XV, right? Because that will force it to be 1. It cannot be 0. For 0, add a singleton clause, XV bar, right? And that's it. That finishes the construction. And this is easy to see that this is satisfiable if and only if, like, the circuit sat instance is satisfiable. Because, so what do you do? In circuit sat instance, you have this graph, whatever, some graph, okay. And basically for each node here, you have a vertex, right? You have a variable. So put that variables, so suppose 1, 0, 1, 1, 0 started from here. So whatever the value here, suppose this was not, this became 1 here. Suppose this was AND, this became 1. This was AND, this became 1, right? So that means if you just put this variable's value to 1, this one's to 1, this one's to 1, and so on, it will exactly evaluate whatever the value was of the was of the circuit sat instance. And similarly from the sat instance, now again you get an assignment and put those values here, and it will actually give the output of the circuit sat instance. You can verify that. So this reduction is actually, because if you see, the problems are very similar, circuit sat and sat. It is just that circuit sat is in the circuit format, sat is in just like clauses format. So you have to just change it to clauses. But still we have not completely reduced it to 3 sat. So we have reduced now circuit sat to a special sat, let's call it sat less than or equal to 3. Sat with clause size at most 3, but we want exactly 3. So what we'll do, since it is transitive, so let's this, what we'll do, we'll reduce this to 3 sat. Okay. And how do we do that? So now we have these singleton or double clauses. So let's say T1 is a singleton clause, T2 is T or T prime is a double clause. So we want to make them 3 variable clauses, right? 3 term clauses. So I need to add 2 here and add 1 here. And if we add just zeros, that is not going to affect. So if we can add Z1 and Z2 such that Z1 is equal to Z2 is equal to 0, then we can add them here. So for T1, what we'll do, singleton clause, what we'll do, T1 or Z1 or Z2. And for T or T prime, what we'll do, just add T or T prime or Z1. Okay. If we can ensure Z1 is equal to Z2 is equal to 0. Because then this clause evaluates to true if and only if T1 is true. This clause evaluates to true if and only if T1, T or T prime evaluates to true, the second clause, right? So what we just need to ensure is that Z1 is equal to Z2 is equal to 0. So what we'll do, we'll take 2 more variables. So we'll take Z1, Z2, Z3, Z4, and we'll add 4 clauses, Zi or Z3 or Z4, basically all 4 combinations of, these guys, Z3 and Z4. So Zi bar, Z3 bar, Z4, Zi bar, Z4 bar, Z3, or let's say Z3, Z4 bar, and Zi, Z3 bar, Z4 bar. So if you add all this, you'll see that Zi is always negative, and no matter what value you take of Z3, Z4, one of these 4 will become 0. Either this will be 0, or this will be 0, or this will be 0, or this will be 0, right? And whenever it becomes 0, the other guy will have to become 1. That means Zi bar has to become 1. That means Zi will have to become 0, right? So we add this for I is equal to 1 and 2. So we add 8 new clauses, and we add these variables to the original clauses and add Z1 and Z2 to singleton and double clauses. And to get a 3 sat instance. And then what we can show is that circuit sat instance K is satisfiable. So let's say that, this formula that you get is phi. So if and only if sat instance phi is satisfiable, right? So that means we have shown that, we have shown the lemma. What does the lemma say? Lemma says that circuit sat reduces to 3 sat, right? Where did we write the lemma? Yeah, okay, here. Circuit sat reduces to 3 sat, right? So we have shown this now. But then, this is very nice because now we know that circuit sat was NP complete. Oh, but we did not show that circuit sat was in NP, but that is not very hard to see because so what can be the certificate for circuit sat? What can be the string T? T is just the, since we are taking the T input here, T is just a string that gives assignment to these nodes in circuit sat. So circuit sat belongs to NP also. So we know that circuit sat is NP complete. Similarly, 3 sat also belongs to NP. We know that it belongs to NP. So 3 sat is NP complete. So we know that and 3 sat reduces to vertex cover and all these. So 3 sat, vertex cover, independent set, set cover, are NP complete. Right? How? Because this is transitive. Because circuit sat to 3 sat, the proof is transitivity. So next time we'll see more problems. More problems which are NP complete. Right? So any question about this, about today's thing? So basically the idea is that, okay, you define this class of NP, which is efficient certificates which are verifiable in polynomial time, small certificates which are verifiable in polynomial time. And then the main idea is that you will get an NP complete problem. You can find an NP complete problem such that any problem in NP reduces to that problem. And that problem is circuit sat. And then you reduce circuit sat to sat, sat to independent set, vertex cover, and then you get this whole chain and all these problems become NP complete. And what does that mean? That none of these can be solved in polynomial time unless P is equal to NP. Or if any of these can be solved in polynomial time, then P is equal to NP. And one of them can be solved in polynomial time if and only if all others can be solved in polynomial time. Right? So any question regarding this? So we have done the hard part now and established the definitions and so on. We'll see a couple of more reductions maybe in next lecture, and then maybe I'll try to see in last 1 or 2 lectures if I want to do something more maybe some more algorithms about NP hard problems. That okay, they cannot be solved in polynomial time, but can we do something with them? Okay, any questions?
Sir, have you received my assignment?
Please send an email about it.
Sir, actually I sent the email on Sunday, so I have not received any reply.
Please forward that to me again. I don't think I got the email maybe. Please send that to me again, and
Yes.
I'll talk to the TAs and figure it out.
Sir, actually I was suffering from dengue, so that's why I could not upload it to Gradescope, and I sent it on Sunday.
Okay, please send it to me. The forward me the email. I'll have a look and let you know.
Okay, sir. Thank you.
Anything else? Okay, if not, then thank you everybody. Happy Diwali to all of you and happy holidays. See you on next Tuesday.